Hello there. Let's do network troubleshooting. Now this video will not have every single thing that can go wrong in a network, nor will it have a full spectrum of solutions. This will cover what CompTIA defines as problems that someone with a Network Plus certification should be able to resolve and fix. So first of all, let's go look at the CompTIA troubleshooting methodology. And the first step is to identify the problem. Now remember, you will be given symptoms. You haven't necessarily got the problem identified just yet. Users are going to be giving you symptoms, telling you what's wrong. Now, with regards to networking, a very useful piece of advice here is who is reporting the problem. If it's just one person, odds are it's their device or their device's connection to the network. Or if there's a group of people, what do they have in common in the network? And that can help you start zoning in on where, networking-wise, the problem may be. Oh, look at that. We've already started falling into the establishing a theory of probable cause. Now, I just want to emphasize one thing. There can be many possible causes, but some of them will be improbable. For instance, if it's a power-related issue for a device or something, there is the possibility lightning may have struck the building. But if there has not been a thunderstorm recently, then that possibility is far less probable. So you can use various forms of logic and thoughts to eliminate what is unlikely to be the cause. Now this does lead to the possibility that you could have multiple theories about what's wrong, and that's okay. But we do encourage that you will deal with one of those theories at a time. So to deal with those theories, you test them to figure out if this is the cause of the problem or not. But please, one at a time. If it turns out that this idea that you tried out didn't work, you go back and you try your next theory. Please be aware though that when you do go back, please undo any changes you have done. That way when you do come across the solution, you know it's exactly this thing I did, and you don't have that niggling doubt of was it the last thing I did or a combination of everything. Combining different theories together is perfectly fine, but do so systematically so that by the end of it you know you do step A, you do step B, you do step F, and that combination solves that problem. Now let's say your test proves your theory is correct. You can move on and establish a plan of action to resolve the issue. Now if you're coming from A+, you might be tempted to say, well, do that plan and implement the solution straight away. But now that you're entering topics like Network Plus and possibly supporting systems that might be working, just not working properly or at their full capacity, you might not be able to implement your solution straight away. You might have to schedule a maintenance period and do this after hours or something like that. But once you do have that plan to solve the issue established, you implement it and you verify the solution. When you are verifying if it's working, please test like a user would use the environment. Don't just check, oh, I can ping something. Navigate to the server. Try and work with the service if you can. That way you know the entire protocol stack or networking suite is working correctly. And when you are verifying the solution, if there is a way to implement a preventative measure to stop this happening again, do so. Because I don't know about you, but I don't want to keep fixing the same problem over and over again if I could do something that would stop it from reoccurring. And then finally, document the issues and the solution you implemented. When you are doing documentation, please don't record things that were completely unrelated to the problem. Document things that were part of the solution, that were the symptoms that were true and accurate to the issue. We don't need a New York Times #1 best-selling novel here. We need a simple, straightforward document that outlines exactly what needs to be done to fix the issue. Alright, so now that we've got the troubleshooting methodology discussed, let's start working our way through various categories and issues. Starting off with cabling issues. So let's have some common cable issues and what their symptoms are. Now these symptoms are not always going to be a perfect fit for, oh yes, it's definitely a cable issue. But you want to probably start at the physical layer of OSI and work your way up. So if people are complaining about slow internet speeds, that is a possible issue with your cabling. Obviously a bad cable, bad termination, or possibly interference on the cable could be slowing down the communications. You could also have a flapping interface. Now, a flapping interface is where the interface is going up and down constantly, which means you're going to have an unstable connection, and overall it's going to appear to be a lot slower, because when you measure the speed over the period of time, when the interface is down, obviously it's not transmitting anything, and that will lower the average speed. You might be experiencing connection timeouts. Please be aware though that timeout errors can be anything from layer 1 up to the transport layer, so don't rule those out possibly. And you could also be experiencing lagging in audio and video data. Now again, that could be a cabling issue, or it could be network congestion, or poor prioritization. There's a whole load of possible causes for these issues. But these symptoms definitely do indicate that we want to start looking at the cabling and work our way up the OSI model or TCP/IP protocol suite, whichever model you prefer. And we suggest you check out the following things as a troubleshooting checklist. Physically inspect the cable and connection that the computer is using, whether it be a desktop, laptop, or server. Obviously, if you're using Wi-Fi, that'll come later. Also, ensure that the connector is properly seated. Don't look at the cable, push it into the network adapter. Make sure it is forming a proper, solid connection. Sometimes the connector can come loose, especially if that little plastic latch has broken off. Push it in properly, make sure it's properly seated. And if you can, try swapping out the cable with a known good cable. When it comes to troubleshooting anything at a physical level, having the ability to test out with a known good will help a lot. If you do have it, try and use a loopback tool as well. A loopback tool is a physical connector that connects the transmitting and the receiving pins together to allow us to simulate communication all the way down onto the wire. It's a little bit better than just pinging the loopback addresses. And if you can, use alternative hosts and ports on the network appliance. So if you can, put another computer on that same connector on the switch, or move the current computer to a different port. You might have to enable a few things, but if you can, move them to another interface and see maybe it's a problem with that particular connector. And then when you're dealing with structured or hidden cabling that might be in your walls, in a drop ceiling or a raised floor, you will have to rely on testing tools, because going into the wall, the ceiling, the floor might not always be a feasible way to do a physical inspection. But even simple physical cable testers can be used to do this testing. And also, check the drivers and the network adapter settings, especially on the client for the drivers. Obviously, if you're connecting to a switch and you're working on the switch, you'll be dealing with the switch's firmware or operating system depending on the class of switch it is. But the types of things you want to check for when it comes to the adapter settings will be the speed, the duplex, and anything else that would affect the physical signaling of data going back and forth between the two devices. Then, a next issue you might have with physical media is attenuation. Now, attenuation will cause the following problems. First of all, attenuation is signal strength dropping off during transmission. The further away something is from the source of the signal, the weaker the received signal will be. With a network cable, you are looking at internal resistance with an electrical cable that will cause the received voltage to be weaker than what the transmitter actually pushed out. The same thing will also happen with wireless, but we will deal with wireless later in the video. You can check the timestamps below if you want to jump to the wireless section now though. You also might experience high impedance causing high attenuation. High impedance is the internal resistance, and some cables may be made poorly, which leads to them offering greater resistance. It's also one of the reasons why we pay attention to the various categories of network cables, because usually the higher the category is, the better it was made, the lower the internal impedance that cable offers us. Also, you might have ran the cable for too long a distance. That's one of the reasons why we pay attention to the maximum cable length, and very often we terminate before we get near that maximum length of the cable. It could also be environmental issues as well. External sources of interference can weaken a signal. So some solutions to attenuation issues will be shorten the cable runs. That way you have less likelihood of a weakened signal arriving at the other end of the cable. If you need to, use devices that offer signal repeating or signal extension. Any network appliance that plugs into a network cable and plugs into a wall socket for power will be able to amplify and repeat the signal. And this can be used to get around the length limitations of some network cables, just at the cost of a bit of latency, as that device has to receive, process, and forward that traffic. And, as I said just now, make sure you're using the right quality of cable. It might be that you use too low quality, maybe you use Cat 5 when you should have used Cat 6. So upgrade to a better quality cable. And try and measure and test your signal attenuation at the installation point, so that you know what to expect, and then you've got a point of comparison to work out, has degradation occurred. Now let's give the interference some attention, seeing as I kept referencing this. So first of all, the issues you will notice will be electromagnetic interference, usually coming from some sort of physical installation, whether it be an air conditioning unit, a light fixture, or power cables carrying reasonably high AC voltages. You also might be experiencing radio frequency interference. Even on a network cable, if the transmission power of a radio signal is strong enough, it can mess with the signal going through it. Network cables can also experience internal interference, commonly known as crosstalk. Remember, with twisted pair network cables, we're twisting the pairs together to try and prevent the one pair inducing electrical current in another pair through electromagnetism. The problem we run into, though, is if those twists start to become undone in the cable, there is an opportunity for electromagnetic interference to occur and induce electrical flow in another wire. And this could have been done by a bad connector or a defective conductor, or possibly the crosstalk is occurring when you untwisted to terminate. That's why we try and untwist as little as possible, or at least cut to length, before we crimp the cable and the connector together. So the solutions we have for this are: use shielded network cables where you can, whether it be foiled or braided, it doesn't matter. Just please also make sure that you do use the shielded RJ45 connectors. Otherwise, the shielding in the cable is only going to be, at best, 50% effective. Also, try and do systematic cable routing and organization so that you know your network cables are kept at least 30 centimeters or 12 inches, depending on which measurement you prefer, away from a source of interference. And use a robust material to avoid strain and bending of the cables. And also try not to twist the cables too much or bend the cables too much during installation. Bend them only as much as you need to. And also do compatibility testing to ensure you're using the right cable for the right situation. And don't be afraid to swap out for a better, higher end cable. Yes, it might cost you more money, it might feel like you wasted some money, but in the long term it will be a better solution. Now, let's move on to switch troubleshooting. So, with the switches, you can start out with some hardware issues. These issues will include the switch has got some power issues. It could have a physical issue with its network adapter. The whole appliance could be faulty. Or it could be that the switch is overheating. Remember, this thing is a computer device, and if we stick it in a network cabinet, we are going to be limiting its airflow if we're not careful. So the solutions to switches having hardware issues are as follows. We can verify that we've got a stable power supply. One thing you might want to do is check that the power coming out of the wall socket is good and stable. Try putting in a kettle and boiling some water. That way you can verify that you are able to get the correct voltage and draw a significant amount of current through that plug with no issue. You also might want to go and maybe check your fuse box or DB box to check that a fuse hasn't blown or a circuit breaker hasn't fallen. But anything that goes wrong behind the wall socket, please call an electrician. Even if you think you can fix it, call an electrician. Also, you might want to consider installing a UPS or a secondary power source to deal with the possibility of unstable power. And make sure that the power supply and cabling connections are correct, solid, and good. One thing you can do, which sounds a bit weird, is sniff the power supply or the fans near where the power connector is on the switch. If you get the distinctive smell of burnt electronics, it's a possibility that that device has got a power supply issue, might have blown, and needs replacing. Also, check to see if there's any damage on your ports and connectors, whether it be for power or for networking. And you know what? A general inspection for damage visibly will help a lot as well, because that can indicate that the device has experienced some significant physical trauma, and that could have caused some damage. Look at your indicator lights and check that there's proper ventilation for the device. And clean out the dust if you have to. This might mean you need to take the switch out, open it up, and blow it out with some compressed air. Just please be aware there might be some warranty stickers there. So before you cut those stickers and start blowing it out, check to see what you might be losing out if you violate the warranty. Assuming it's still under warranty, obviously. Then the next thing you want to do is check what the status indicator lights are telling you on the switch. Problem is though, the color of the status lights will vary by vendor, but generally green and orange lights are the most popular. You might come across blue and red in some vendors, but overall, I'd say majority of switches use green and orange. Now, also the way the lights work will usually vary a little bit from vendor to vendor. So if it's a solid color, normally that means the interface is on and it's working, but there's no traffic. If it's flickering or blinking very rapidly, that normally means the interface is up and it's transmitting data, no trouble, if it's blinking very rapidly. If it's a solid bad color, as I say, so let's say green is the good color, orange would be the bad color. If orange is the good color, then something else might be the bad color, or it being off would be the indicator of a problem. Now, usually when it's solid color and it's meant to be a bad color, that indicates the interface is physically on, but something is causing a logical block on the interface. Whether it be a misconfiguration or a security violation, can't be sure, but it does give you something to work with and start looking at for identifying the problem. If the blinking is a bad color, it normally means there's some sort of fault that was detected. Again, this can vary by vendor. It could mean a physical fault, it could mean a logical fault, there's a whole bunch. And if there is no light at all, it means it's not connected, which could indicate that there is a fault or break in the cable as it's not receiving any electrical signals from the other side. But as I said just now, the coloring and the blinking can vary by vendor. So it might be useful to check the support documentation or manual for that switch. Possibly even keeping a laminated sheet of the status lights attached to every switch or in the cabinet where the switches are, so that anybody could check what the status lights mean when they're trying to troubleshoot something physically without having to go and track down where the document is. Now, you can also use a couple commands to diagnose what's going on with switches, and again, syntax will vary by vendor, but anytime you're looking at using commands on a network appliance, you should expect the commands to differ a little bit from one vendor to the next. But some common types of commands to use will include commands that we can use to show the device's configuration, to see the device's interfaces configuration. Now, the device configuration would be the whole device versus the interface would be just that one interface. Also, we have commands that will allow us to see the device's interface statuses in detail. And we can also run commands to look at all of the interfaces at once, whether it just be general status information, VLAN information, or information to do with spanning tree protocol and any of its variations. You also want to check out what the MAC address table looks like, because the issue the switch might be encountering could be related to its learning and usage of the MAC address table. And as we discussed in the security videos for networking, there are some options to make your switches ports a bit more secure, and the switches port security could have kicked in, causing the symptom that we are now being told is a troubleshooting issue. If it turns out that this is a security breach or an attempted security breach, this would be something we would need to escalate to the security team or the incident response team, depending on how your organization structures its IT security department. Now, when you are busy reviewing some of these commands, you need to have a close look at some of the interface statuses. Now, usually your interfaces will have two states displayed. The first one is usually the physical status of the interface, and the second one is usually its logical status. So in the case of a switch, it would be layer 2 details. And if we're talking about routers, it would probably be layer 2, layer 3. Now, it'll usually be indicated as a up-down pair of words. So if it says down and down, normally it means physically down, no physical connectivity. And this means that the logical state will also be pulled down, because you can't do anything logically on an interface if it's not physically working. I can't type a document on my computer if my computer is turned off. Makes sense now, doesn't it? If it says administratively down on either of the two, that normally means the interface has been shut down via a command, or it was a port security reaction to an unrecognized MAC address. If the interface says up down, physically it's fine, but there's a logical error. And if it says up up, it's all good. which means we need to move on to another idea to figure out what could be wrong with the switch. Some of the things that could go wrong is we could be having loops and broadcast storms. Now the problem that we run into with loops and broadcast storms is STP does exist, but it won't always be there to save the day. For instance, unmanaged switches usually don't support STP, and if they do, you get very little control over it. And sometimes you might be dealing with manageable switches from enterprise vendors that don't run STP by default, which sounds weird, crazy, and maybe a little bit irresponsible, but it's the way the vendor decided the default config should work. And this has caught me out a few times in the past before, because the first few network vendors I got exposed to always ran STP by default, and I was under the impression, well, that's just a good practice everybody does, until I found some vendors that didn't, and I got a nasty shock. Thankfully though, I was able to figure out the problem very quickly and just turn STP back on. Or there's the possibility that for whatever reason, spanning tree protocol might have been disabled. In the case of data center networking, because of the spine and leaf topologies design, we get redundancy without the likelihood of loops occurring if it's done properly. So spanning tree protocol might have been turned off because in that situation there would be no need then to rely on something that would cause an interruption to communications while STP converges and sorts out the logical loops. So the solution would either be to go and physically eliminate the loop or turn STP back on. If the convergence time of STP is the issue, consider using RSTP. It's faster. And then we could also be having a power over Ethernet issue or a PoE issue. Now with PoE or power over Ethernet, you must make sure you're using Cat5e or higher. You can't use an older category cable. And even if the cable installed that you want to run power over Ethernet through is of Cat5e or higher, is it an old cable? I might be a bit nervous about running power through the brown and blue pair of wires in an old cable, as the cable has deteriorated over time. So it might be a good idea to look at using a newer cable. We also have something called a PoE budget, or a power over Ethernet budget. Your switches will be one of the sources for power over Ethernet, and it can output a certain amount of power over a certain number of interfaces. So if you have got too many devices drawing power on the interfaces, you might not be able to have as many as you want, especially when you have a variety of PoE standards, because with some of the newer standards, they draw more power, and then that will obviously eat away from the budget. A lower power setting, you could probably have more interfaces offering power over Ethernet in the PoE budget than if you have some interfaces using one of the newer, higher power standards. And then you could also run into a standard mismatch. A lot of the switches will allow you to specify which PoE standard it must work with on which interface. And if I've got a very high power device on the end of the cable, but I use something like 802.3 AF, which only does 15 watts, I might not be providing enough power to the end device. Now, the end devices can be things like wireless access points, voice over IP phones, physical phones, IP cameras, and a variety of other lightweight, fairly small end devices. And obviously you need to double check whether you're doing 802.3 AF or PoE, 802.3 AT or PoE Plus, or 802.3 BT or PoE++, because you're looking at 15.4, 30, and 60 to 100 watts on those three standards respectively. But with that out the way, let's go look at some IP troubleshooting now. Now, before we start going crazy with fixing routers and stuff like that, let's just talk about some of the commands we can use to diagnose and troubleshoot the issues. And first on the list is the notorious ipconfig command, which is a Windows command. And there are some useful variations of it. ipconfig will just show you basic interface info, as in IP address, subnet mask, default gateway, and that's mostly it. If you run ipconfig/all, it will show you a lot more detail. It will show you MAC addresses, IPv6 and IPv4 info, DHCP server address, DNS server listings. It shows you everything you could want to know about every network adapter's IP configuration. Then ipconfig/renew triggers a DHCP lease renewal. So instead of waiting for the timer and expiration, you trigger the lease renewal right away. If you run the command ipconfig release, you give the IP address back to the DHCP server. Now, due to the DHCP server and Windows clients trying to do what's called preferential addresses, where the server will keep aside the address for you in case you come back and give it back to you so that you get some consistency with DHCP address allocation, when you run ipconfig release, you'll give the address back to the server and it'll probably end up coming right back to you before you have a chance to even run ipconfig again. So then why do we need it? Well, maybe we've got a duplicate address error where the same IP address is being used by two devices in the network. So the solution would be to take the address out of the DHCP pool by making it an excluded address. The client that gets the address through DHCP will then get a new one. But you'd have to run the release command on that client to give the old one back. Now there will only be one instance of that IP address on the network, and you can then track and trace it and figure out how it happened and deal with the responsible person appropriately. Please be aware, torture is not condoned. Then you've also got the flush DNS command option, and that is quite useful later on when we're troubleshooting DNS, because what it does is it empties the DNS resolver cache on Windows. Like most operating systems, Windows will keep a copy of the answers you get from a DNS server when you're resolving names, and as such, it'll check that cache answer rather than doing a query every time. So it's always a good idea to flush the DNS records if you're troubleshooting a name resolution issue, which can possibly be very closely related to IP troubleshooting issues. Then you get ifconfig, which is a Unix-Linux variation. Please watch out because it is one letter difference between the Windows and Linux command. Although this is now considered an old command and being phased out in a lot of Unix and Linux distributions and variants, CompTIA might still use that as a way to try and just trick you between one character's difference between Microsoft's IP config and Linux's IF config. Now, it can be used to check interface address details and assign IP address and other configuration information to an interface. Honestly, the things you can do with some of these Unix and Linux commands is quite lengthy and probably wouldn't fit comfortably into a single video like this. So I suggest check out the man pages or the info pages to see various options and how to use them. It's a very, very powerful command set. But I did say ifconfig is starting to get phased out in the Unix and Linux space. It is being phased out in favor of the new IP command. Now, again, Unix Linux, and it's meant to be the successor to ifconfig. And you can use it to check details for IP addressing and your routing or gateway settings, as well as apply the settings for IP addressing and routing and gateway settings. And again, because there's so much things you can do with this command, it's probably going to be easier for you to go check out the man pages or info pages for this command. Then we have the ARP command, or the Address Resolution Protocol command. This command is present in Windows, Unix, and Linux systems. And the options will vary by the OS, but overall it does let you see that ARP table. And it can also let you go and check the results of the Address Resolution Protocol, or even modify the table entries manually. Please note though, that unused entries that are learnt dynamically do get removed after a period of time, depending on the operating system. So not seeing a particular IP address MAC address association in an ARP table doesn't mean that ARP is not working. It just means that you might not have spoken to that device for, let's say, 5 minutes. And the operating system removed that entry to empty the address table and make it more reliable, more stable, and in certain ways more secure. So it's not a completely conclusive result if you use ARP to troubleshoot something. And then we got the one that everybody's waiting for, ping. Ping is available on Windows, Linux, and Unix systems, and again, the options and behavior will vary by operating system a little bit. But what it does is it sends a simple IP message to the destination that elicits a reply. Strictly speaking, ping is utilizing a layer 3 protocol called ICMP, or Internet Control Messaging Protocol. And when you send a ping, you are sending what's called an ICMP echo request. The recipient of that will reply to you with an ICMP echo reply. It's basically just an empty message going, hello, and the recipient goes, hello, back to you. And it's very useful, but remember, it is verifying layer 3 connectivity. It is proving that I can get a packet to a destination. After layer 3, it doesn't really do much to test the communications. There could be an issue at the transport layer, at the session layer, at the presentation layer, or at the application layer. and ping doesn't really do great at helping us verify that. But hey, I can ping a web server and prove, okay, we can get a packet there. So that means the issue might be something to do with the web service running on the server, if we're not getting the web page to load. But nonetheless though, with ping, we can target the host with either its IP address, its host name, or a fully qualified domain name if it is an internet or public entity. Now, ping's outputs can be pretty useful if you spend some time interpreting them correctly. When the output is resulting in a success, it normally shows you statistics around the performance of the traffic with latency measurements, and also gives you an indicator of the TTL field's values. If you get an error message, the error message will normally indicate roughly where the issue may be, such as host unresponsive, network unreachable, something like that. So read the error message and apply the error message to what you understand about the network and networking in general. It will help a lot to figure out where an issue may be. You can also use ping in what's called a progressive ping test, where you will first ping a 127 IP address. Most people go 127.0.0.1 because it's quicker to type. And what you've done is you've proven that your TCP IP services are installed and working correctly, which nowadays they usually are. Then you would ping your own IP address to check that, okay, that is working fine as well. After that, you might want to ping a neighboring host in the same LAN segment as you to see if you get a reply or not. Then you would ping your default gateway to see if you can get a packet to the router. And then you might want to try pinging another host in a different local subnet. So in other words, another LAN segment that the router could get you to check that at least internal routing is working fine. Then you might want to ping a host in a destination subnet that you're trying to get to. Not necessarily the intended destination, but another device in that same network to see if you can get a message to something else in that same network. And finally, ping the destination host. I would suggest try and do it by IP address rather than a host name, because then at least you're just testing basic IP connectivity. If you try and do it by the host name, you're mixing DNS and name resolution troubleshooting with IP troubleshooting. Not saying don't do it, but try to test one thing at a time systematically. And if you can get a packet there by the destination IP address, then try the host name. And if you get a failure there, you're actually dealing with a name resolution issue, which we'll look at in a little bit. Then you have tracert or traceroute, depending on the operating system that you are using. If you're using Windows, it's normally tracert, and if you're using Unix or Linux, it's normally traceroute, full word ROUTE. What's quite cool about tracert or traceroute is it's utilizing the same underlying protocol as the ping, which is ICMP. And the way it works is it gets us the IP address, sometimes the host name, of each router or layer 3 device in a route to a given destination. And this is amazingly helpful if you know what route your traffic is meant to be going through. And this means that if you see a different series of IP addresses being used, it might be that you're going through a different route, which could be the cause of the problem. Or if you keep getting asterisk responses, that could be indicative of a failure in that route. I normally wait till I have 2 or more results that have asterisks instead of IP addresses before I panic, as some routers can be set to not reply to ICMP echo requests. Speaking of routers, let's look at troubleshooting router issues. Now, a good checklist to run through for troubleshooting your routers will be to check that there is basic connectivity. Make sure that the power cables are working fine, and then check your data cables are properly plugged in and there's no visible issues. Then, similar to the switch, log in and verify status information on your interfaces. Check the physical and the layer 2 details, and then the IP configurations that would probably have been applied to them. And then check the IP addressing and configuration that would have been applied to them. Also, it might be a good idea to compare to what the hosts are being configured to use. Common mistake I've seen being made is one particular IP address gets configured on a router's interface to act as a default gateway, and then somebody misconfigures the default gateway setting on the clients or the DHCP pool. And the clients will then be forwarding traffic to the wrong gateway, the wrong layer 3 device. So, worth checking that. Also, because it's a router, check your routing table entries to make sure that stuff looks correctly entered and routes determined. Whether those routes be done manually or dynamically, it doesn't matter. Check the routing table and see if it aligns with what the network should be doing. This is one of the reasons why network documentation does matter. Helps a lot with the troubleshooting. Then review the routing configuration, whether you've done static routing or dynamic routing. Check the config, and in the case of dynamic routing, check the status of the dynamic routing protocol that you are using. And check to see if access control lists are present, and then obviously go and check the access control list to see if that might be causing a problem with the router forwarding certain traffic or all traffic. And also, same applies for a routing policy. Routing policies are closely related to ACLs, but they're normally a little bit more advanced, in which case then you escalate to a higher level of network support. Then we can move on to DNS troubleshooting. As DNS and name resolution is incredibly useful in networking nowadays, and if things go wrong, that can lead to some major issues. So let's look at the commands that we can use for DNS troubleshooting. First of all, you could look at doing a ping on the host name, and that will result in DNS going and getting the IP address so that the ping can actually work. Or you could use NSLookup, which is available on Windows and some Linux distributions. When you do use NSLookup, please remember two things. Firstly, it's a command line application. Once you've typed NSLookup, you're in a utility where any names you've typed will be attempted to be resolved through DNS. And any IP addresses you type in will be again attempted as a resolution with a reverse lookup, IP to name. And you do need to remember to type exit to leave this command line utility. Otherwise, if you're on a Unix Linux system that doesn't support NSLookup, you could use a tool like dig to test a domain name. Cool thing with dig is you just say dig and the name you want to test, and then it does a simple once-off lookup and you're back to a normal command line. Now, what kind of issues could we encounter with DNS that we need to fix? Well, first of all, you could encounter a timeout on a response. DNS itself doesn't time out, but the thing that wants DNS to get the name, to convert it into an IP address, is what could be causing the timeout. You could be experiencing a DNS redirection issue, where you typed this name, you connect, and then you get redirected to another site. That makes me concerned around a few things, but it is a potential issue. You also might have entries in your local hosts file. Windows, Unix, Linux, various operating systems have a text file usually tucked away somewhere under a system directory or folder, called hosts or something to that effect. It's an ordinary text file where you can go in there and you can type any name you like, tab, and then any IP address. And that is a local name resolution service that your computer could be using. Now, depending on operating system or changes to the operating system settings, that host file might be checked before DNS. And if a name is found in that file, that's the name and IP address combo that will be used. DNS would not actually be utilized if it was tested before or used before. Also, you might be getting results from an old response that is being kept in your cache. Hence why I mentioned the ipconfig /flush DNS earlier in this video. You also might be trying to get an authoritative answer for security purposes, but the DNS server you're talking to does not have the start of authority record configured on it, or it's misconfigured, one of the two. You also might have a service record that you're looking for specifically that is missing, such as an MX record for email services or an SRV record for very particular services. Also, a DNS record update might have been overlooked during a change. You might have moved a particular service to another IP address, but people forgot to go and update the DNS record. So the DNS server is giving the correct answer, at least as far as its records are concerned, but the records are out of date. It's like if you get a new phone number, but you don't tell people what your new phone number is. Don't be surprised when they try and call you on your old number. You need to update their records too. And you might have a primary DNS failure, and the secondary DNS server does not have the desired records. For instance, a lot of organizations will make a primary DNS server an internal private one that just resolves internal private servers. And their secondary DNS server or servers might be public root DNS servers. But the thing is, when you're trying to resolve an internal private host name, the public DNS server doesn't have that record. So it's not going to be able to answer you. And there is also the possibility that DNS filtering might be blocking the requested record. Now, in a lot of cases, the issues start to move from client to server. So apart from having just the incorrect server being configured on the client side, more often than not, DNS issues do require some level of escalation. And then, moving along to the wireless side of things, wireless troubleshooting can be a lot of fun because you are dealing with a media that by its very nature is more prone to interference and is less stable. In fact, I personally prefer wired connectivity. My desktop running a network cable. My laptops, generally I plug a network cable in if I'm sitting at my desk. Wireless only gives us one major benefit that a network cable doesn't, and that is convenience. The problem is, though, to get that convenience where I can connect anywhere, there's a lot of possible problems that can happen with that radio signal. So, let's figure out what wireless performance issues can pop up. And as I said, bear in mind, wireless is an unstable media. It will fluctuate for a variety of reasons, not all of which are problems, but more side effects of a network being used. So some important metrics that will be useful for us in troubleshooting will be bitrate and throughput. What type of megabits per second, gigabits per second is our wireless network card reporting to us? And what kind of speeds are we actually getting through the wireless connection? Because remember, your bitrate and bandwidth is maximum potential, whereas throughput is what are you actually getting when you're transmitting the real data, the real packets. Then attenuation, another important thing to measure. Signal strength correlates directly with performance. The weaker your signal, the lower the speed is. That's why when we were running through the wireless LAN standards or the Wi-Fi standards, every time I quoted a speed, that was the maximum potential speed that you would experience given a very good signal. If you are very far away from the wireless access point and your signal is very weak, your data rate will be dropped down accordingly with the weakened signal. And it might not always just be distance, it could be the obstacles between you and the access point as well that has a greater impact on the received signal strength on the client. There's also the possibility that you've got interference. Now, when you're dealing with interference, you can measure something called a signal-to-noise ratio, which lets you measure how strong is the signal in relation to any sort of interference signals near the frequency that your access point is working at. You will probably need some specialized tools to do that. But in general, your two main tools would either be a radio frequency spectrum analyzer. That is the fancy one that you would want to use for things like true, accurate signal and measuring SNR. Otherwise, a wireless client with an appropriate application would be pretty much okay. Just remember though, you are dealing with a client and a network card that is of questionable quality. And even if the quality is good, well, you get variations. Your smartphone, for instance, will have a weaker wireless transceiver than a laptop does. So be prepared for different types of results from the same position with the same access point but using different clients. Now, wireless performance normally can be a big indicator of an insufficient coverage issue. The causes of insufficient coverage would be things like signals being blocked due to physical obstacles in the premises, or a greater than optimal distance from the access points. There could also be electronic interference nearby from things like microwave ovens or cordless telephones that make the wireless coverage area shorter. Some of the solutions that you can look at implementing to improve the coverage issue is to extend coverage with more access points. You can look at using wireless range extenders, but they generally are going to be receiving a weaker signal and then repeating it. And also there's a lot of security concerns around wireless repeaters. It'll be better to rather deploy a second proper access point, whether it be a small office, home office, or a proper enterprise, and then cabling that additional wireless access point up to the rest of the network infrastructure. You could look at also maybe using a more optimal antenna for the situation. For instance, outdoor antennas being used indoors, not ideal. Directional antenna being used when you intended omnidirectional coverage, not ideal. Use the best antenna for the current job. Also, you might want to go and check out the TPC or transmit power control settings and adjust those. Somebody might have lowered the transmission power control, shrinking the effective coverage area. Please note though, if it has been lowered, you want to just check why was it lowered, because it might have been lowered for a reason besides performance. And account for and resolve any wireless client congestion issues. The more people that associate with a wireless access point, the more people have to share the channel and the bandwidth and the channel time with each other. And if you're asking 64 people to take turns with something, that's going to take a lot longer before you get your turn to transmit data than if there's only 6 people trying to take a turn with the wireless access point. So deal with that as best you can. Either reposition the users or add more access points to congested areas where the users are likely to congregate. Other issues you might be encountering that affect performance is the wireless channels overlapping. Now, you will experience this issue more with the 2.4 GHz frequency band than the 5 GHz band. So generally we suggest in the 2.4 GHz band, look at favoring channels 1, 6, and 11 to minimize on that. And also try not to do channel bonding with 2.4 GHz when you're making multiple channels work together. Yes, you do improve performance, but you run greater risk of channel overlap messing with 2.4. If you want good performance and you want to do channel bonding and all that good stuff, that's when you want to move to the 5 GHz band. The channels were divided way better there, and the channel bonding will not cause any surprise issues for you. Also, if you're planning to provide coverage overlap between multiple access points, try and keep the overlapping area of coverage around 30% so that there is enough overlapping coverage for somebody who's moving from one access point to another access point's coverage area to be smoothly handed over without being too overlapping and causing co-channel or neighbor interference. To achieve this, you might want to lower transmission power. That's why I said if the transmission power has been lowered, go and check why, because turning it back up again might just bring back another problem. You could also look at repositioning the access point, either closer to each other or further away from each other to achieve the 25 to 30% optimal coverage between two APs. Then you could be encountering interference issues, whether it be co-channel interference, where you and another person are using the same channel next to each other and you can't control each other's APs, or adjacent channel interference, where I'm using channel 1 and somebody in the next building from me might be using channel 2 or 3, which overlap and cause adjacency issues. Now this issue might be that you've got neighboring clients on the same or overlapping channels that are outside of your administrative control. This is going to be a headache, but you can just move to a different channel that is far away from the neighboring devices that are outside of your network. You could also try checking for physical signal blockage being a cause for interference. The structure and the furniture can be blocking, reflecting, or weakening a signal, depending on what it's made of and how thick that material is. You could also be experiencing electromagnetic interference, where it's normally going to be appliances and devices that work at similar channels or frequencies to what Wi-Fi works at. For instance, microwave ovens with very bad shielding are highly likely to cause EMI and mess with wireless signal whenever somebody's busy reheating something. So the solutions for this, you could either reposition your access points, make frequency and channel adjustments, or try and identify those EMI sources. You might need a radio frequency spectrum analyzer to do that, and then you deal with those sources appropriately. Another wireless issue you might encounter would be roaming and disassociation issues. So you could run into what's called a sticky client, which is a client that fails to switch over to an access point for better connectivity. It sticks to its original home AP and refuses to disconnect from it and reconnect to an AP that's nearer with a better signal. You could be dealing with a flapping client. This is a client that frequently switches between APs, often unnecessarily. Now, a flapping client might just be a result of the person is sitting at the exact perfect balancing point where two overlapping APs of coverage area are providing the exact same signal strength, and the client's not moving any closer to one or the other. So it might alternate between the two. That'll be fun. It could also be that your access points lack support for an appropriate roaming standard, or even the clients might also be the issue with the roaming standard. The three main standards for roaming are 802.11k, R, and V. Your roaming and disassociation issues could also be caused by a malicious attack, such as a hacker launching a deauth attack, hoping to make it a bit easier to try and capture the authentication and encryption information that they would need to bypass your wireless security. Solutions to these common issues can include adjusting settings on the wireless LAN controller, especially for roaming, reviewing any event logs and details on the network infrastructure, and if accessible and available on the clients as well, and then look at implementing a security measure if the roaming issues or disassociation seem to be originating from a security threat issue. Now, besides doing troubleshooting, you also want to look at doing some network monitoring. so that you know whether your network is performing well or badly, and you could start trying to resolve issues before the users start logging support tickets. I mean, how cool would it be when the user phones and says, there's a problem with the network, and you can reply with, I know, we're halfway to fixing it already. I mean, how cool does that sound? So let's try and use some tools to help us here do this nice monitoring. So first up, you might want to do some traffic capture so that you can analyze it and understand how your network's behaving. Now, you will need an application that is able to record all traffic that arrives on a host computer's network card. Generally, remember, when traffic arrives on a computer, if it's not destined for that computer, the computer will figure it out at some point. Maybe the destination IP is wrong, maybe the port's wrong, something like that. And it will throw the traffic away because, well, it's not destined for it. Certain applications that I'll tell you about now will be able to say, no, don't throw that away. I want to record that so we can review it. And the cool thing is you can review the headers for all the layers of your networking services, and you can even look at the payload of the message, assuming it's unencrypted. You might be able to review the payload of an encrypted frame or packet, but there's a lot of things to unpack there. Firstly, do you have the decryption key? Secondly, do you have the legal right and authority to do that? So let's just go with the fact that you can look at an unencrypted payload and we'll pretend that there's no way around the encrypted payload, even though there might be. There are popular tools, though, that we can use to do this. If you're using Unix and Linux, TCP dump is a common go-to option. You can also use ngrep, network grepping, Unix Linux origin, or my personal favorite, Wireshark. A few reasons why Wireshark is my favorite. Mostly free and open source, but most importantly, available on Windows, Unix, Linux, Mac. So it doesn't matter what you're using, you can use Wireshark. That to me is amazingly valuable. Also, it does have a GUI tool which can make a little bit of the analysis a bit easier to scroll through and skim through stuff, especially with the color coding that it offers on the user interface. Now, to do a good traffic capture, you are going to want to deploy it carefully in the network. So if we look at a network like this, and I run Wireshark or something like that on this computer, all I'm getting is whatever's coming and going on this network card. That is it. Now, if people aren't talking to me, I can't see what they're communicating. I can't monitor the network in a larger space or a larger capacity. I might rather want to capture stuff coming and going on this router's interface, because that could be a lot more useful and reveal more information about what's going on this network. So to do that, I can go and purchase something called a test access point, or a TAP. It's essentially a 3-interface device, possibly more. Interfaces can be present, but it'll have at least 3. That allows for a pass-through to occur, and then for me to bring along a monitoring station and cable that in. If I run Wireshark or something there, I will be able to capture traffic, because whatever comes or goes through this tap, a copy gets sent out of that interface. Now, we could monitor what's going on in this LAN segment, whether they be 2 computers or 20 computers or 200 computers. We could have a lot more insight into what's going on in that LAN segment. The problem, though, is taps are kind of expensive, and speed-wise, they might not be working as fast as your connection needs to work. So, alternatively, we could use a managed switch. If the switch over here allows me to log in and configure stuff, I can come along with my inspection machine, my monitoring station, whatever I want to call it, and cable it up. And then I do something called switch port analyzer or port mirroring, and I'll probably do it on that interface. Now, what port mirroring will do for this interface is whatever comes and goes on that switch's interface, a copy gets sent out of this interface down to that computer. This computer can be running any sort of traffic monitoring tool like Wireshark, ngrep, or TCP dump, and that would allow me to see what's coming and going on the LAN segment. And the nice thing is, because it's part of the switch's capabilities, the switch would not necessarily slow things down, and whatever speed this link works at, the switch will be working at that speed. Unlike the tap, which could be working a lot slower than that link. So that's 2 ways that you could go about doing this. I'll leave it up to you, but please do me one favor. Make sure that you do this with authorization and permission, because technically you are intercepting communications, and that could lead to a privacy or a legal issue. Make sure this is done with intent and understanding. Then we got traffic monitoring. Traffic monitoring is where we try to continuously observe and analyze the flow of traffic going across the entire network to ensure optimal performance and security. This will allow us to identify the various traffic trends that we have, like when does our network seem to be busy, when does it seem to be quiet, when do particular protocols seem to be in a higher proportion of utilization, stuff like that. And if we monitor the performance effectively, we can use it to detect anomalies within our network. These anomalies could be early warning signs of a problem or a failure about to occur, or a potential security issue. And because we have better understanding and insight and the ability to understand how is our network doing, it'll help a lot with our network capacity planning and making design adjustments for future improvements. Now, usually we use something called flow data that can be used to get this holistic view of my network traffic. You get protocol services called NetFlow and similar services that can be used to do this. You need an appliance that supports it though. But when you do have an appliance that supports it, what will happen is NetFlow or similar protocols can report the network activity on the appliance and its interfaces to a central server. That server can then consolidate what that one appliance has told it with what other appliances are telling it to give that holistic view of your network's activity. But whenever it comes to some sort of monitoring for comparison purposes, you need a baseline of comparison. You need what is normal and what is normal at this period of time, so that when you are going to compare in the future, you're comparing apples with apples. Then you'll want to look at doing some traffic and bandwidth testing to see how well your network copes. Now this, you're using applications that simulate network traffic and test the performance of the various network components. And this can help you identify bottlenecks and capacity limits in your network. This type of testing will include packet generators, network emulators, and throughput testers, such as iPerf and other similar tools. But something to understand about traffic and bandwidth testing tools is they are creating a synthetic workload. And this means the results may or may not really align with how the network will handle real traffic. For instance, if you do something like doing one of those internet-based speed tests, that's showing your network maximum potential, but it's not a real download or upload, because if I'm downloading a file from a web server, that server decides how fast I download something, not my internet connection. And if my internet connection is way faster than what the server I'm downloading from says I may download at, doesn't matter whether my internet connection is 1 gig or 10 gigabits, I'll be downloading at whatever the server says. So these testing tools are great to indicate how well your network can cope with different types of traffic and volumes of traffic, but it's not always going to be a perfect fit. It's more of an indicative test and result than a true result. Nonetheless though, that should be enough for troubleshooting at the Network Plus level. As I said at the beginning of this video, this is not an exhaustive section, but it's enough to get you going, give you some pointers, and help make you a bit more of a better troubleshooting professional when it comes to networking support. You will learn so much more when you do this in the field and when you start looking at other networking courses that might be further along in your career trajectory, but this will be enough for a good start. I'd like to say thank you all for watching. I really appreciate this. If you have any friends, family members, colleagues, or peers that could or would also like to learn Network Plus, don't be afraid to share this with them. Otherwise though, I'll catch you in the next video.